In this lecture, we will talk about circuit configurations for modulation and demodulation process. We will start our discussion with generation of TSB-C AM signal. This is the circuit diagram for generating TSB-C AM signal. We provide the message signal and the carrier AC cos omega ct as two sources. So the total input is message plus carrier signal. The signal is then passed through the diode. Now diode will pass the signal when the input is positive and block when negative. Here are two signals involved in the input to the diode. One is carrier and another one is message. Here carrier frequency is much higher than the message frequency. And also for using this circuit, AC must be greater than empty. Then the operation of diode switching will be controlled by the carrier itself. When the input is passed through the diode, a multiplication operation takes place. The input signal is multiplied by Wt. Wt has a shape like this. It is a square wave with only two values, 0 and 1. 1 when the diode is on and letting the input to pass, and 0 when the diode is off and the signal is not passing through the diode. As the switching operation depends on the carrier, the frequency of Wt will also be omega c. So the signal at point B or V prime BB is AC cos omega ct plus mt multiplied by Wt. Wt has a Fourier series expansion like this. The Fourier series was taught in the signals course, so I am not going into the detail, but one thing, the fundamental frequency of this Fourier series is omega c. That is because the switching operation is controlled by the carrier signal and the carrier frequency was also omega c. Now we are replacing this omega t in this equation by this Fourier series expansion and we will get this. Now multiplying these two signals, we can reach this equation. Obviously, there are some other higher terms containing odd frequencies of omega c like 5 omega c, 7 omega c. We are ignoring them because they will be eventually suppressed by a filter in the next stage. Now there is a cos square omega ct term. We know the formula of 2 cos square x, which is 1 plus cos 2x. We are applying this formula to cos square omega c and we will reach this equation. This is the output at point B. This signal is then passed through a band pass filter with center frequency omega c. So the only components that have frequencies of omega c or closer to omega c will be passed and other low and high frequency components will be blocked. Here you can see this has a frequency of omega c, so this component will be passed. This is message signal and the frequency of message is much lower than the omega c, so this will be blocked. Again there are two components here. First one is a DC component 1 by pi AC, as DC has 0 frequency, so this will be blocked. Then comes cos 2 omega c. This has higher frequency than omega c because the frequency is 2 omega c here. This will also be blocked. Now this is the term where the frequency is closer to omega c because mt is the message and its frequency is omega m, which is much lower than omega c. So the all over frequency of this term is much closer to omega c. So this will be passed. And further on, all the components will have 3 omega c, 5 omega c, 7 omega c and higher order terms. So they will be also eventually blocked. So the final output of the band pass filter is V prime c ct, which is half AC cos omega ct plus 2 by pi mt cos omega ct. As you can notice, this is our carrier, half AC cos omega ct. There is a multiplier half which will not be a problem. This is the carrier component AC cos omega ct. And this is 2 by pi mt cos omega ct. You can ignore 2 pi because this is also a multiplier and will not matter. The main part is mt cos omega ct, which is modulated carrier. So this is our expression of DSB-C AM signal and we can use this circuit for producing this signal. Now we will talk about recovering the message signal from the modulated signal. The first circuit for doing this is rectifier modulator. The circuit diagram is shown here. The input is the modulated signal which is passed through a diode. So like the previous slide, the modulated signal will be multiplied by Wt. If we use the Fourier series expansion for multiplication, we will get this result: 1 by pi into AC plus MT plus other high frequency terms, which involves omega c, 3 omega c, 5 omega c, 7 omega c, and etc. odd multiple of omega c terms. But as this output is passed through a low pass filter of cutoff omega c, all the frequency components equal or above omega c will be blocked. So only 1 by pi AC plus MT term will be passed. Then it is passed through a DC blocking capacitor, which blocks the DC component AC, and the final output is 1 by pi MT. Here the typical wave shapes at different stage of this circuit are shown. The input is this modulated signal having low frequency envelope and high frequency carrier in between. When it is passed through the diode, the signal is rectified and the diode works as a half wave rectifier. A multiplier 1 by pi is introduced, which we can see from the equation, so the signal loses some strength. Then it is passed through the low pass filter, so the high frequency component inside is blocked and only the low frequency envelope is passed. And finally, the DC blocking capacitor removes the DC component, and this is the final signal, which is 1 by pi MT. Don't worry about the factor 1 by pi. We can get rid of this using an amplifier. One important note, this method will be applicable for mu less than or equal to 1. I encourage you to investigate why this cannot be used if mu is greater than 1. Our next demodulation circuit is an envelope detector, which is basically a half wave rectifier with a filter capacitor. I hope you already know the functionalities of a half wave rectifier circuit. The input to the circuit is the modulated AM signal, then comes a diode, and then one capacitor and a resistance in parallel. Let's see what happens here. Initially, the capacitor is not charged. As the input signal increases on the positive side, the diode is forward biased and the current passes through the capacitor and gets it charged to the maximum value of the cycle. Then, when the input signal falls beyond its peak and starts decreasing, the diode is now reverse biased because the P terminal of the diode is connected to the input, which is now less than the N terminal, which is the capacitor voltage. As the diode is reverse biased, the capacitor starts to discharge to the resistor, and in the meantime the input is increasing again. At some point, the input just passes the decaying capacitor voltage and the diode again gets forward biased and charges the capacitor to the peak value of the cycle. This goes on, and the final output is nothing but an approximation of the envelope, but with some ripple. This ripple can be minimized by carefully choosing the values of R and C. For proper reconstruction, RC must be much greater than the time period of the signal, which is 1 by omega c. Also, RC needs to be less than the inverse of 2 pi into message bandwidth. If you choose an RC too small, the ripple will be very high. If you choose an RC too large, the output will not be a proper representation of the signal envelope. Finally, the last type of demodulator circuit we are going to talk about here is synchronous detector. It has other names like coherent detector or homodyne detector. The operation of this demodulator is the simplest. You just have to multiply the modulated signal by cos omega ct carrier. So the output of the multiplier will be AC plus MT cos square omega ct. If we apply the formula of 2 cos square omega ct, which is 1 plus cos 2 omega ct, we will get this: half into AC plus MT into 1 plus cos 2 omega ct. After passing through the low pass filter with a cutoff frequency of omega c, this component with 2 omega c frequency will be blocked. So the output of the low pass filter will be AC by 2 plus half into empty. Then the DC blocking capacitor will block the DC part AC by 2, and the final output is the message empty multiplied by some multiplier, in this case half. Two key observations here. For previous two methods, mu needed to be less than or equal to 1, but this method can be used for any mu value. Another key point: whenever you will build a modulator circuit, you may need a bandpass filter of omega c frequency, and for demodulator, you may need a low pass filter of omega c cutoff. Even though its operation is very simple, implementing the circuit is very complex, as you have a multiplier here. But previous circuits simply required only diodes and capacitors. A summary of this DSB-C AM section. Now we know that DSB-C type of AM has very low efficiency, at most 33% if we want to ensure envelope detection. Also, in the case of DSB-C, both upper and lower sideband is transmitted. That's why it's called double sideband. But this is bandwidth inefficient, as both the sidebands have similar information, and if we could pass only one of the sidebands, we would be able to reconstruct the message. AM is more vulnerable to noise than FM. Finally, the modulator and demodulator used for DSB-C AM are very simple and less expensive to implement. That was all about DSB-C. In the next lecture, we will start our discussion on single sideband amplitude modulation. Thank you.